This video will be focusing on how to draw a free body diagram for mechanic statics. The video is essentially a revision video that is assuming that you have covered all the material in mechanic statics. The reason for this video is even until the end of the semester when I do the quiz for the students, there are still some students that is making huge mistake in drawing free body diagrams. So I hope that this will help for preparing for the final exam. Now, if you are watching ahead of time, meaning that you are still covering each chapter and you want to watch this one, feel free to watch. Hopefully it will serve as, a correct mind setting for you to be able to draw free body diagram correctly for each topic. So without further ado, let's go straight into it. First and foremost, what is a free body diagram? If you notice, there are three words in the term free body diagram. Free body diagram. So obviously it is a diagram, that's number one. Number two, it is a diagram of a body, a specific body. And number three, it should be free. Meaning what? Meaning free from all the surrounding elements, all the surrounding bodies. Right? So it is a diagram of a specific body that is free from any elements that is the surrounding elements. Right? So it should be only that body and all the forces acting on the body. So that is free body diagram. Now that you have understand what is a free body diagram, the next thing to know is what are the steps for drawing free body diagram. Step number one, answer this question. Which body? Which body? Now, in any given problem, normally there are multiple elements, multiple things that is interacting with each other. And you have to determine which element, which thing that is you considering as your body for that particular free body diagram. Now we will cover some examples after this, but this is the first step, determining which body. Step number two, draw the outline of the body. This is straightforward, draw the outline of the body. Number three, draw all the forces that is acting on that body. This may include the weight if the weight is given. Please take note that each forces have its own value of the force, the magnitude of the force, and the direction. So both elements or both information should be there in your free body diagram. Number four, any known values should be written or stated in the free body diagram. For example, if the weight of the element or the object is given, it should be drawn and labeled with the value in the free body diagram. If the force acting on that element is known, is given by the question, that value have to be put into the free body diagram. Number five, label all the unknowns properly. Label all the unknowns properly. So of course, in any given problem, you have some known value that is given by the question, and you have the unknown value that you have to determine and calculate in the question, right? So all the unknown should be labeled properly. Now, in terms of the label, there are some labels that are commonly used. For example, if you have external forces acting on a body, normally they use P. If there's cable and there's tension in it, normally you use T. If you have normal reaction, normally they will use N. If you have friction, normally you will use F. If you have pin support, which have, in 2D you have X and Y component of the forces, normally you will use the label of the point as the notation for the force. For example, at point A you have AX, AY, at point B you have BX, BY. So those are some of the common labels that tend to be used. So please try to use labels that are easily understood by the examiner for the exam purposes. Now, there are several different types of equilibrium problem that would require you to draw free body diagram. Of course, every equilibrium problem would require you to draw a free body diagram. Of course, we have covered many topics in many chapters that is basically equilibrium problem. We have covered equilibrium of a particle, we have covered equilibrium of rigid bodies. This is where you are introduced to understand how to draw the support reactions. And then you have trusses, you have frames, you have machines, and then you also have learned about internal loading, and then of course you have also learned about friction. Of course, friction is actually part of rigid body, but a new element added to it is the existence of friction. Now we will cover some examples to illustrate how to draw the free body diagram for each of these type of problems and each topic, inshallah. Now take a look at this example. Of course, I'm not putting a proper question here. I'm just focusing on drawing a particular free body diagram. So by this diagram, you should be able to identify that this is where you will apply equilibrium of a particle, because normally it will be equilibrium of this point or both, depending on the question. So now this problem is about equilibrium of a particle. Now we will go step by step of how to draw the free body diagram. If you remember, the first step is to determine which body, right? So here, whether it is ring B or ring D or both, right? So for example, if the question would require you to draw both of these free body diagram separately, of course. So let's say here we draw free body diagram of ring B, right? So that's number one, determine which body. Okay, body B, the ring here. And then second, draw the outline of the body. So for a particle, the body is simply that. You can draw something like that or something like a ring. So that's the outline of the body. The body is complete. Then number three, draw all the forces. In this case, you have the forces in this direction. Oops. Okay, sorry for the direction. But I hope you get what are you meant to do, right? Okay, so you have all the forces, and then you have to label properly. So for example, here TBC or FBC, and then here FBA, and then here FBD, and then you have the angle 45 degrees, and then you have the angle 30 degrees, right? So of course, normally there will be some known values that is given by the question. So in case, for example, let's say the weight of this is already given as 100 Newton, for example, right? So in this case, at this free body diagram, all are unknown, so there's no known, right? So again, step by step, draw the body you have drawn, select the body. So here the body is ring B, draw all the forces, all the unknown and all the known. The angle is known here, right? So another free body diagram of point D. So the body is D itself, and then all the forces. So you have, okay, so you have here, and then you have here. So let's say this is known, so you have 100 Newton as a known value, and then you have T CD or DC, and then T. Okay, why am I using T and F? Let me use F all, then it's easier. So and then FBD. So this is 45 degrees. Oh, and this is 30 degrees. There you go. So this is simple, right? This is a revision. So just to illustrate what you do with the understanding of the step by step, right? So the selecting of the body for equilibrium of a particle normally is not that complicated, because it's quite obvious normally. We will later on see for other topics, sometimes some students struggle to determine or to identify which body should be the free body diagram. Anyway, so this is equilibrium of a particle. Moving on. Now this next question is equilibrium of a rigid body problem, right? So you have two members connected here. So one is member BD and then member ABC. Now depending on the question, you have to determine which body or which of the member you decide as the body of the free body diagram. Normally it will be ABC. Now, in total, there are several options of body that you can take. One is member B, D, right? One is member A, B, C, something like that. And one is actually combination of member A, B, C still attached to member B, D. Right, this is as a body, right? All of these three is, it can be accepted as, the selected body of your free body diagram. However, if you select this one, normally it's not useful because you cannot actually solve what you want to solve, because of the number of unknown will be more than the number of equation that you have. Hence, that is why normally we separate all the bodies involved. So that's the reason. It's not that this free body diagram is wrong. It is correct, but it is not helpful for you to solve anything. So if you want to illustrate, so because this is pin, so you have two unknown there, and then this is also pin, you have two unknown there. So in total you will have 4 unknown, right? And you have only 3 equation from one free body diagram, so you cannot solve. So now, first thing, when you separate, you have to be able to understand that this is a 2 force member, so it's either in tension or in compression. So of course, logically, if you can understand how this mechanism work, if you're pulling this way, this member will be under tension, right? So free body diagram, if you draw free body diagram of member BD, if you draw it, so it is 2, so it's 45 degrees, right? So if you draw the forces, it will be under tension in the 45 degrees, and you can label this FBD, the same magnitude, right? So if you know this, it will implicate the next body. So free body diagram of member A, B, C. So it is something, so you have a force here which is 400 Newton. This is known, and then at point A you have, let's say, AX and AY. We assume the direction, so it is here at point B. So this is this direction, so this will be this direction, FBD, and then you have 45 degrees, right? And also you have to put all the dimensions, of course. So you have 0.5 meter and another 0.2 meter, right? And then this one is 0.1 meter. Okay, sorry for the messy handwriting because the positioning of this is not ergonomic enough. Anyway, so a tips here to know whether the free body diagram is complete is that when you do this equation of equilibrium afterwards, all the elements that is in your equilibrium equation of equilibrium should be existing in the free body diagram. For example, when you do summation of fx equal to 0, let's say positive right towards right, and then you have 400 here, for example, and then for this one we'll have minus fbd cos 45 degrees, right? And then plus ax equal to 0. Now, so ax should be here, fbd should be here, 45 degrees should be here, right? So that's one way to understand what element should be here. Now, another one is when you do summation of moment, let's say about a equal to 0, right? Let's say you take counterclockwise as positive. Now, when you calculate for moment, for example, this 400, now you have to have this distance, right? So you have minus 400 and then 0.5, 0.2, 0.7, right? So if you do this calculation and you realize that, oh, the distance is not drawn in the free body diagram, meaning that your free body diagram is not complete. You have to have the distance. So anything that you use in equation of equilibrium should be existing in the free body diagram. Some students, for whatever reason, have a different label between the free body diagram and the equation. That does not make sense, because the equation of equilibrium is referring to the free body diagram. So if I'm the examiner in the exam, if any label is not tally, I just consider that as wrong, because I will ask, where is this? What do you mean by this? Because it's not in free body diagram, and then etc. Right? So make sure you understand that. Next, this is an image of a truss, right? Of a truss. Now, for a truss, depending on which method that you use, right? Because we have a method of sections and method of joints. So for example, if you do method of joints, we are focusing at each joint, right? So you'll draw a free body diagram of a particle basically. And if you do method of section, basically you cut wherever you want to cut. So depending on which method that you use or which method the question asks you to use, make sure you know what you need to do. But either way, in many cases for trusses, you actually have to solve support reaction first before you can solve for all the forces in the member, right? To solve for support reaction, normally you would require a free body diagram of the whole trusses, right? So you have the whole thing, and in this case you have the force here and force here, and then you have the unknown support reaction there, and then unknown here, right? So example ND, AX, AY, and then you have 300 Newton, and then you have 300 Newton, and of course all the dimension you have to put, right? So now from here you solve the support reaction, and then you go, and for example if you are using method of joints, so for example you start from point A, so you have this one, you already have AX and AY, and then you have all of this and so on, right? So this is a free body diagram of the whole truss, this is free body diagram of point A, for example, right? So make sure you understand what's going on, and make sure you understand why we can actually use this kind of method of joints. Basically is similar to equilibrium of a particle. The only reason we can use this for truss and not for frame or machine is because we know all of the members are two force member, right? Because for any two force member, it can be either in tension or in compression. Hence, you always have, for example, at this point, you always have force here, force here, force here, and force here, be it tension or compression. But if this is a frame or machine, that is not the case, because for every pin, you have X and Y support reaction or forces. Next, let's take a look at this. Let's consider this as a frame. And this involves this I don't know, this wheel, for example, right? Now, when you have some wheel like this, or if you have pulley, I noticed that some students become confused as what to do with it, right? So there are two possibilities or two options basically, right? Whether you want to take all this wheel together with this member, as one body, or if you want to take this wheel as a separate body than this body, right? So the free body diagram will be different. So let's consider this. If you take this as one body, so you have one body here. Okay. You can understand, right? So this I'm not sure how to label this. Okay, this is one free body diagram, and then there's another one here, together with the wheel, right? So you have two free body diagram to solve this one. If you select to separate, so basically you have one here, and then one wheel over here, and then you have this thing here, right? So we'll do one by one. So if you have this one, of course here in this case we have AX, AY already given here. Maybe it's originally have a pin support, for example. Now here, basically you detach this point and this point, right? So basically you have X and Y reaction, same magnitude, opposite direction, right? So for example, if you because there's no point here, right? So let me call this D. So if you have here, like for example, dx and going down dy, for example, so here we'll have dx and going up dy, right? It should be opposite with the same force. And then Okay, here Cx is already given. So here, okay, you have also 20 Newton given by the question. Now, here is where when you take separate it, so you have normal reaction here, right? So basically, this one will feel that the wheel is pressing it here. So let's call this N wheel, for example, and then you will have here N wheel, and there you go. Because this one, it will feel like the wheel is pushing it, while here it feel that this curve is supporting it upwards, right? So that is your free body diagram, of course, all the dimensions, etc. Now, if you are separating it, of course, the rest is the same. So you have this one. So you have, if you use this one, right? Now, this force, if you have it here, right? For example, 20 Newton. Now, when you separate this, of course, here is what you have just now. That's the same. But what you do when you separate this at this point pin, so you have actually X and Y here, right? For example, you have let's say what's we call this D, right? So let's call this E. So you have, for example, EX, EY. So you'll have the opposite, EX, EY. That is what will happen. Now, in this case, it will be quite interesting because this 20 Newton is acting on this. So there will be dispute whether it should be here or it should be here, right? So sometimes people actually draw in the middle the pin that is attached to both, and it is acting on a pin. Okay, so normally that's why I tend to do it this way. I rarely disconnected the pulley or the wheel because there's no need for disconnecting it, because it creates more unknown than, unless you actually have to solve this. If you have to solve this, then you have to disconnect. But if you just have to solve here or here, for example, then this is sufficient. So make sure you understand that. Alright, moving on. Now, if you look at this diagram here, you will notice that there's a point here. This is normally when the question will ask you for internal loading. So meaning you have to cut here, right? So before you cut, so basically just like, for example, the truss, you have to understand that sometimes you have to solve the support reaction first. For example, you need to solve this one first. So you have to take everything as a total first. So in that case, you have a free body diagram of let's say this is a beam AB, right? The whole thing. So you have the beam, oops, and then you have AX, AY, for example, for the pin, and then you have normal direction B, and then you have to convert this distributed loading to a single point loading. So it's 9 kilonewton per meter times 3 meter, right? And then you get something 9 times 8, 27 kilonewton. That is this force. And then you have another force of 12 kilonewton here, and you have all the distance. You have to put it, and then you can solve for all of this, right? Using summation of fx, summation of fy, and summation of moment equal to 0. Now, after you have solved that, you can determine whether you want to use it on the right or on the left, or if the question asks you to use both, you have to comply. But make sure, if you want to do this, do not cut after you have drawn this, because many students make that mistake, right? Because they have already converted this distributed loading into one single point, and then they cut after that. No. You have to cut, and then you convert distributed loading. So meaning that after you cut, because you cut at C, right? So actually there's a distributed loading on this half, and there's distributed load. Okay, this is until the end, right? So it will be something like that. Only then, basically, you convert it into one force. So basically, this distributed loading here have one force here. This distributed loading here have one force here. Make sure you understand what you are doing, right? Do not cut from here. It's not a valid. it's not valid if you do that. You have to cut and then convert the distributed loading accordingly, right? And the rest, you know what to do, right? So you have N, you have V, and then you have a moment, right? Okay, I'm drawing messy here, but I think you know what you need to do. Now, normally if you look at this kind of diagram, you know that this will be about friction. In this case, sometimes there are different possibility, right? Possibility. So in this case, for example, possibility 1 is tip first, possibility 2 is slip first. Now, additional to when you draw the free body diagram, additional to which body, right? Which body? There's also the question of possibilities, and you have to know that one first, because each of these have its own free body diagram. You cannot use the same free body diagram for multiple options or multiple possibilities, because in this, the free body diagram will be different than this. So each possibility will have its own free body diagram. Make sure you understand that. For example, in tip first, we know that the normal reaction is there, right? And the friction is not yet maximum normally, right? So this is tip first. So this is fundamentally different than slip first, which is the assumption is N is not yet at the edge, but F is the maximum, right? F max or mu as N, right? So this is a fundamental difference where this distance is known, this distance unknown, right? This F max is basically known, especially if the coefficient of static friction is known. This force is not known, right? So free body diagram, the two free body diagram here and here is fundamentally different. You cannot just draw something and then suddenly calculate for tip first and then suddenly calculate for slip first. This is wrong, because then both equation will not be valid with respect to the free body diagram. This is another example of a friction problem, right? And here, is there any possibility, right? Or sometimes the question is giving different, how to say, different situation, different circumstances. For example, in this case, this let's call this a beam or rod or something, right? For example, rod is about to fall down, or rod is about to slide up. For example, because we have force here, right? So one possibility is that this force is big enough that this is moving up. One possibility is, for example, this have its own weight, etc., that this is sliding down. What is the difference? If it is sliding up, so of course if we consider both of these is not smooth, if both have friction, so when you draw the free body diagram, if this is sliding up, you have a friction in that direction, right? Because it's countering the movement. When it is sliding down, the free body diagram, the friction is on that direction because it's countering the sliding down. Of course, you have all the normal reaction, etc., right? And then you have P as well. So you have P, you have the normal reaction, and if you have the weight, if you have the weight, right? So make sure you understand what the question is saying, what the question is giving, so that you have the correct friction direction, right? That's crucial. In your free body diagram, the friction is not, the direction of the friction is not assumption, right? You have to know the direction correctly, otherwise it will affect your calculation. Now, this is another possibility where there are two different object or two different thing that is interacting with one another, right? So this guy here is, in this case, it is running. This is one type of exercise, I think, while pushing this weight which have friction here, right? So which body? So the first question in drawing free body diagram is which body, right? So this is the case. There is a possibility that you are interested in this body, so you draw this body, or you're interested in that body, so you draw this body, or both basically, but separately, or this body, meaning that this man together with this weight as one single body. That is my free body diagram. Is this correct? Yes, it is correct. In terms of free body diagram, it can be correct. But normally, why? So if I ask the question, why we normally do not draw this? Because it does not help us to solve. Why? Because normally there will be friction here. There will be friction here. There's normal force, of course. If you consider this is even more. The number of unknown will be more than the 3 equation that we have, right? Because we only have one free body diagram, so only 3 equation: force Fx, force Fy, and moment, right? So why normally we separate? Because we have 2 free body diagram. You have 3 equation for this free body diagram, and you have 3 equation for this free body diagram, right? So in this case, you have the friction here, normal reaction there, and normally this guy have its own weight, and here because it's pushing, so the counter is like that, right? While this is feeling the push, and then it's have its own weight and the friction and normal reaction. It depends. If this is like 2 different contact, then it's much more complicated because you have more unknown. And sometimes it's just you are pushing a box, so it's just 1 and 1, something like that, right? So this is an example of, you know, when we say which body, the first question in drawing your free body diagram, which body, this is an example of a question where you have to determine which body do I need to solve. Right? Sometimes the question only require you to solve this one. For example, if it doesn't want to know what is friction is here, etc., sometimes this is sufficient, but most of the time, or because it depends on the question really. Anyway, so I hope the illustration here helped. Okay, here is basically a different type of working out or exercise. So of course the difference here is that because this one, if you draw the body here, it is being pulled in that direction, while for this guy here, it have the resistance that way, right? And then you have the friction. Okay, which direction is the friction? You'll have here, right? And then the friction is there. So I hope you can understand why, for example, why is this friction going forward while this friction is moving backward, right? So I hope you can imagine what is happening, or you imagine what you are trying to do, right? So if you are having this motion, if this is slippery, right? One way to understand logically is, if this floor is totally slippery, your leg will be moving that direction, and you will fall. So if that is the tendency for your leg, of course the friction is in that direction, making it stable if the floor is rough enough. Similarly here, right? This will be, if it's being pulled, it want to move there. That's why the friction is countering there. In this case, if this floor is slippery, right? This feet will slip that way, right? So then you know the friction is countering it in that direction. Right. Similarly here, this is being pushed that direction, friction is this direction. So all of this, hopefully you understand what's going on, so that you know how to draw free body diagram correctly. So there you go, some illustration of how to draw free body diagram for different topics that we have covered in statics. Hopefully that helped. Any comment or further improvement for this kind of video, feel free to share, and with that, all the best for you in your studies, in your exam, and see you next time, inshallah.